Welcome to today's lecture. Today we are going to continue from where we had left in the previous lecture. After learning the basics of machine foundations in the previous 8 lectures, today we are going to learn the methods of analysis applicable on machine foundations. The methods for analysis of block foundations can be classified as empirical and theoretical. The empirical methods don't have a theoretical basis and are basically based on the cumulative field experience of engineers and experts. Sometimes they have thumb rules as their basis. So usually the empirical methods of analysis are preferred for less important foundations or for preliminary level analysis and design. The theoretical methods for analysis of block type machine foundations can be classified into 3 categories. The first category of theoretical methods are based on modeling the soil underlying the machine foundation block as a semi-infinite elastic medium. The second type of theoretical methods, they model the soil as a finite spring and damper. The third category of the analysis methods is basically called as the Barkan's approach and is much simplified as compared to the first 2. Let us see each of these methods, especially their fundamentals. Now in the first method, that is, which treats the soil as a semi-infinite elastic medium, it is assumed that soil actively participates in the vibrations as a continuum medium. It's a bit difficult to model. So its pictorial representation is shown here, that we have the concrete block on which the machine is operating, and then the vibrations are being transmitted radially outwards from the bottom of the block foundation into the soil. So a particular region of the soil in the form of a sphere participates in the vibrations. So as of now, less understanding is available for this method of analysis, so still it has not become the mainstream among the practicing engineers. The second approach basically assumes that the block is being supported by spring damper represented by soil as shown here. A very important feature of the approach is that here the mass m which you are seeing is not just the mass of the block and the machine. Here the mass of the soil participating into vibrations is also considered. So that makes the process bit difficult. So as of now, for this method also, the understanding level is not very high, and still this method is not in the mainstream practice. Now, as compared to these two methods, the Barkan's approach considers the soil as a lumped spring. The important feature is that it considers the damping contribution as 0 and also the mass contribution of soil to be 0. So these are ignored, so that makes the method simplified as compared to the other two. So as of now, this has been the most popular among the theoretical methods. Its simplicity basically makes it more understandable and adaptable by engineers. Also, the results have so far been found to have good correlation with experimental observations. Rather, the results are slightly on the conservative side. Hence, this has been the most popular method, and in this course we'll follow this approach. Before going deeper, let's try to understand the various types of vibrations a block type machine foundation is subjected to. As we have studied before, the block type foundation is subjected to vertical vibrations, horizontal vibrations, rocking, pitching, which are basically rotational vibrations, and then yawning, which is the torsional vibration. Now, as far as the vertical vibrations are concerned, if we have a machine foundation with the machine resting on the top such that the center of gravity of the machine, the dynamic loads imparted by the machine, the center of gravity of the block, and that of the base, if they are all in one vertical line, then pure vertical vibrations are generated. Because in such condition of operation, there won't be any rocking vibrations or pitching vibrations associated with the vertical loading. So as such, the vertical vibrations will be independent of other types of vibrations and will be uncoupled. Even if there is now a horizontal load acting on the machine foundation, its effect will be independent of the vertical vibrations. Now let us also study other types of vibrations. And let's say we have the machine resting on the top of block type foundation, but if it's generating horizontal forces, a reciprocating type machine reciprocating in the horizontal direction, then it will not just induce sliding, because the horizontal force is acting at some height above the center of gravity of the entire system, so there would be a bending moment also associated. Because of this reason, sliding and rocking or pitching, they are always coupled. So we just want to highlight that rocking is basically the rotational vibrations which are in the plane of the sheet, and pitching are the vibrations which are out of the plane of the sheet. So we will be dealing with sliding and rocking, and same kind of treatment shall be there for sliding and pitching, but the two are coupled. Now let us also see the behavior under yawning. So for this purpose we are showing the same block in plan. Now how this kind of yawning vibrations are produced, let's understand the various scenarios possible. The first scenario is that if we have a pair of oppositely directed forces with a distance between them, and here the forces are dynamic in nature, so that means the two forces are produced by reciprocating machines which are running out of phase. So when one machine undergoes the motion on the positive side, the other one goes in the opposite direction. Now such a combination will induce pure yawning in the block foundation. It will not produce any sliding or rocking or pitching. So the expression for the amplitude of the torque can be written as the product of the force amplitude multiplied by the distance separating them in plan. Let us see another possibility. How about a machine which is rotating type and where the mass is rotating in the horizontal plane? Will this kind of arrangement produce any yawning? So here we are showing the plan with x and the y axis. Z is of course horizontal and coming out of the plane of the sheet, and let's say there is a mass which is undergoing anti-clockwise rotation with a constant angular frequency. So what will be the effect of this rotating mass whose angular frequency is omega m and constant? Will it produce any yawning? Now if we analyze carefully, basically this imparts a centrifugal force on the foundation system going out from the center of rotation to the particle, and the amplitude of the force would be the eccentric mass multiplied by the radius a and the square of the angular frequency. Now the direction of the force is continuously changing in the horizontal plane. So as such, this action is producing horizontal forces in both the x and y direction simultaneously. So basically the effect would be that it will produce sliding coupled with both rocking and pitching. However, this will not induce any yawning. But let us consider another extension. If the mass is replaced by a pair of equal eccentric masses and both of them are now undergoing circular motion as shown here with equal angular frequency, then the effect will be that of counterbalancing, provided the individual radii of the circular motions are also equal. So here no yawning will be produced. However, if the angular velocity is not constant, that is, if the two rotating masses are undergoing angular acceleration, which is the rate of change of the angular velocity, which is also the second derivative of the angle theta, in this particular scenario there will be a horizontal torque produced. And the magnitude of this torque will be given by the product of the eccentric mass, the angular acceleration, and square of the radius of motion. The factor 2 comes here because there are two masses undergoing this rotation. The presence of the two masses basically nullifies the horizontal component, and hence the associated sliding and rocking or pitching. So the overall conclusion of the analysis we have presented so far is that the vertical vibrations and the yawning vibrations, they are uncoupled and they can be analyzed independent of other types of vibrations. Let us see the computational procedure for analyzing the vibrations of the block for vertical vibrations and yawning. Now, as far as the vertical vibrations are concerned, the equation of motion is mz double dot plus kz equal to the acting force pz t in the z direction, which is pz dot, the amplitude multiplied by sine omega m t. So please note here that we are ignoring damping, so that's why we have the mass m and the stiffness k. So here for this particular case we can very easily obtain the natural frequency of vibrations in the vertical directions simply as under root kz by m. So here kz is basically given by the product of cz and the area of the base of the foundation, and m is the mass of the machine plus the block. Similarly, we can obtain the amplitude of vibrations. For this, we first obtain the static amplitude as the ratio of the force amplitude by the stiffness and multiplied by the amplification factor A omega. Or alternately, we can use the other equation involving the modified amplification factor. So here, because the damping ratio is 0, so the amplification factor is simply 1 divided by 1 minus r square. Now if we use the other relation involving modified amplification factor, then we have the mass ratio, that is the eccentric mass to the overall mass multiplied by the modified amplification factor and the eccentricity. So here we have A dash omega m as the modified amplification factor, which is now for the special case equal to r square divided by 1 minus r square. So R is already defined as the frequency ratio Fm to Fn. Now the code IS 2974 recommends that we should avoid the zone in between 0.4 and 1.5 for the frequency ratio. That is the frequency check, and then the amplitude should be within the limits prescribed by again IS 2974 part 1. In the same manner, we can write the equations for the case of yawning. So just to recapitulate, this is how the yawning occurs. So basically, yawning is the rotational type of vibration about the vertical z-axis as shown here, about which the torque is acting. Torque is sinusoidal in nature with amplitude T naught. So for this case, we can similarly write the equation of motion as shown here. So here in place of m, we have the mass moment of inertia because rotation is involved. So phi z, the mass moment of inertia multiplied by theta z double dot, which is the second derivative with respect to time, plus k phi theta z equal to the torque, which can be expressed as sine function, and the amplitude is T naught. So here the solution is very much similar as for the case of the vertical vibrations. So the k phi, the stiffness, is basically c phi into the polar moment of inertia we have already explained, and phi z is the mass moment of inertia. All these terms are already explained to you. So here you can very easily write the expressions for the natural frequency and also the amplitude as in the case of the vertical vibrations. So note that here theta z double dot is angular acceleration analogous to the linear acceleration along z axis. So here we can write the expression for angular frequency. So that will be the omega theta z n. So theta z refers to the rotational vibrations about z axis. So that is the under root of k phi by phi z. And again the units are radians per second. Similarly, we can write the amplitude. So here the amplitude of the vibrations will be in the form of angular displacement. So this is written as a theta z naught, and that will be equal to the product of the static amplitude, which is the ratio of the applied torque amplitude to the stiffness multiplied by the amplification factor A omega. So now we have to convert the angular amplitude into the displacement amplitude. So we are just drawing the foundation block in plan for easy visualization. So let's say we are showing here the center of rotation, and if we join the center of rotation to one corner, then here the direction of the motion of the farthest point in the horizontal plane is shown. So if the coordinates of this point are known, x0, y0, then we can write the expressions for the displacement amplitude in terms of the angular amplitude as we are writing here. So basically, for getting the y component of the displacement, we have to multiply the angular displacement amplitude with the x coordinate, and similarly to obtain the x component, we multiply the angular displacement amplitude with the y coordinate of the point. So once we have the x and y components of the displacement amplitude, we can obtain the net displacement amplitude as the under root of the sum of squares of the x and y components. So basically, when we talk of the displacement amplitude check, or the limits on the displacement amplitude, we have to check this component. So thank you very much. If you have any questions, you can discuss them during our interaction in the MST.